All right, so we've now covered the general trends for ionization energy, atomic radius. We've talked about ionic radius. We've talked about electronegativity. And we've covered the principal rules that you have to use to explain the differences in those trends based on effective nuclear charge or effective nuclear attraction. Okay? However, there are some of these periodic trends that have odd exceptions to the general trend. And you're supposed to be aware of them really just for ionization energy. But I'm also going to talk about the other property, electron affinity, in this table as well, or in this video as well, because it has some similar ideas. So the general trend across the period from left to right for ionization energy is clearly that it increases. We look across any of these groups, any of these periods of the periodic table, and it's clearly a major increase as we go across. And our reasoning for that is that as we go across, the principal energy levels are the same in all these elements, so they have equal shielding effect. However, with increasing protons, there's an increasing effective nuclear attraction for the valence electrons, and that means more energy is required to remove the electrons. And going down a group, we see that essentially there's a decrease from hydrogen to lithium to sodium, potassium. Also the same here, from helium to neon to argon to krypton. And you can see that that difference sort of starts to become less and less, and that's because the energy levels converge and get closer and closer together. So all those rules are still holding true. But as we go down, we're getting more and more principal energy levels, therefore more shielding effect, which means the outer electrons are less attracted to the nucleus and they are more easily removed. But there are odd exceptions, as I said before, and those odd exceptions are these funny dips that happen, and they seem to happen again and again. Less significantly here, but still a bit out of the ordinary, okay? And yeah, there's a dip here, okay? You wouldn't really be asked to explain these ones so far down the table, so we're gonna kind of forget about it for now, but although it would be based on the same ideas. If we think about what elements these are, this is between element 4, which is beryllium, and element 5, which is boron. And then so boron, carbon, this is nitrogen, and this is oxygen, okay? Now we're looking at the same columns down below, so we're looking at magnesium versus aluminum, and we're looking at phosphorus versus sulfur. Okay, so we've got those rules about effective nuclear attraction, and those are great for the general trend. However, here we have to look a little bit more closely, and it helps if we can look at the electron configurations. So for Be, the electron configuration is 1s2, 2s2, and for boron, for boron, let me fix myself here. For boron, we've got 1s2, 2s2, 2p1. Okay? If I superscript, I think I made a little mistake. We're going to fix it. 2s, I can do it. There we go, 2s, there we go. Okay, so those are the configurations for beryllium and for boron. Now, if you think about what's different about them, in boron, we have an electron in a brand new sublevel. This is the first time that there's been any p electrons in any atom. Boron's the first one to have a p electron. And so the p orbitals, or the p sublevel, as we can call it, all three p orbitals together is called the p sublevel. The p sublevel is slightly farther from the nucleus than the s sublevel. It's slightly higher energy. On average, the electrons are a little bit farther away in the p sublevel than they are in the s sublevel. And one of the basic rules about attraction and charge is if electrons are farther away from the nucleus, they're going to experience less attraction. So the p sublevel is slightly farther from the nucleus. So the valence, the p1 electron in boron experiences less effective nuclear attraction than the s2 electron in beryllium. Okay, so I mean it's the same basic principles, but now we're looking much more carefully at the electron configurations. Okay, and you could probably not say p1; you could just say the p electron in boron, and look at what I've done now. We're going to just do this. P electron in boron experiences less effective nuclear attraction than the s electron in beryllium. And that's simply because it's a little bit farther away on average, or you could say it experiences very slight shielding from, not the full shielding effect because they are in the same energy level, but it does experience a slight shielding from that s electron, from the two s electron. Right, but both of them add up to the fact that this p electron is less attracted to the nucleus than these s electrons are, and that's why we see this dip. This would be identical reasoning for magnesium versus aluminum. Why we see this in the next spot as well. Okay. Okay, but then then it goes up, and I guess the reasoning there, why does it go then up for carbon, is that, well, carbon has a sixth proton, and so eventually you're increasing the protons, and that can outweigh the fact that you're putting things into the p level. Between boron and carbon, if we were to add carbon into the mix, carbon experiences its p electrons experience the same. What happened? Copy. We got this. So carbon's electrons experience the same amount of shielding as boron's electron, but there's an extra proton. So we would expect the charge or the ionization energy to go up for carbon because there's more protons in that nucleus. So not really usually what you have to explain, but just in case you had that question about why. Okay, if we think about the next exception was for nitrogen to oxygen. It helps for this one if you draw an orbital diagram. I'm not going to do that just based on this video and trying to do it quickly, relatively quickly. But if we've got, let me take these back down, having a lot of troubles. There's nitrogen is 1s2, 2s2, 2p3, and oxygen is 1s2, 2p4. Now, if you remember what those orbital diagrams look like, when you have 3 p electrons, the p sublevel is half full in nitrogen. Okay? And so for oxygen, oxygen has 2 p electrons forced to pair up in the same orbital. Well, we talked about that a little bit, that the pairing up causes extra repulsion between oxygen's electrons. And if you have repulsion, that's going to take away from attraction. So as a result of having that extra paired up electron, the oxygen's electrons experience less attraction to the nucleus. So the reasoning is slightly different, but both of these exceptions to the general trend, the reasoning comes down to the specifics of their electron configurations and their orbital diagrams. So being able to think about what we talked about in the last topic, atomic structure, in detail, you can connect it here. So again, the exceptions are because, one, we've got the first p electron slightly farther from the nucleus, slightly shielded by the inner 2s, slightly inner 2s electrons, and therefore the p electron is less attracted and can be removed easier. And in this one, the oxygen's last electron has been forced to double up in the same orbital, which causes extra repulsion and therefore less attraction. And so it's easier to remove one from oxygen than nitrogen. So those are the exceptions to the ionization energy trend. Another property that is sort of new for the IB to talk about is the electron affinity. You should be aware of what it is. It's the energy released when a gaseous atom gains an electron. So when atoms are forced to gain electrons, usually it actually releases energy and it stabilizes the atom somewhat to accept electrons. So to show this value for oxygen, we would show O as a gas plus an electron makes O as a gas, but now it has a minus charge, just a 1 minus charge. Even though O forms a 2 minus ion, if you're showing the electron affinity, you are just showing 1 electron being gained. Okay, so these values are written as energy values, energy per mole, and they're written as energy values. So the bigger the electron affinity, the more energy released. That's a more negative enthalpy change, is what it's described as. So more energy gets released when there's a bigger electron affinity. Okay, and more energy released means there was a stronger attraction that was allowed to be formed. So a stronger attraction for electrons equals a bigger electron affinity. And when I say bigger, I mean greater in magnitude. So this property is a little bit confusing because of the negative, because we haven't talked about enthalpy yet in much detail. But essentially what you see is it's going to look like the opposite of ionization energy. That the elements to the right, we know that the elements that are to the right of the periodic table have the highest effective nuclear attraction, because for their row, for the same PEL, they have the most protons. And so we would expect that the elements at the right of each row would have high electron affinity values. They have the strongest attraction for electrons. Therefore, when they gain electrons, they release the most energy. And so it's pretty similar in that way to ionization energy, or really to electronegativity. The highest values are fluorine and chlorine, and this one would be bromine. Okay. Now, there's a bunch of gaps, and those gaps are pretty much repeating these dips, right? The gaps in the dips are exactly what we were looking at in the ionization energy trend, that beryllium doesn't get an electron affinity. Beryllium doesn't tend to gain electrons. It's hard to make beryllium gain electrons because it would turn it into this configuration, which is less stable. Same thing for nitrogen. Nitrogen with that half full P sublevel isn't very likely to gain electrons that become P4. That wouldn't really be stabilizing. And so you can actually see that nitrogen isn't listed. Nitrogen, you can think of it as going all the way back to 0 for that dip, right? And then this would be the dip back down here before we get to boron. So beryllium is basically doesn't exist. Nitrogen doesn't exist. It means that you can't really make them gain electrons. Now, I don't think you need to explain this discrepancy, these exceptions to the trend for electron affinity. I think just knowing essentially what electron affinity is, knowing how to represent it in an equation, and understanding that it's a pretty similar rule. The general trends, the things that increase attraction, effective nuclear attraction, which is less principal energy levels and more protons, means a bigger electron affinity, a more negative electron affinity. And so that will increase in magnitude down to the halogens, group 17. And the noble gases don't have these values because you can't force a noble gas to take on an extra electron, because it would have to go to a new principal energy level, and it wouldn't be attracted enough to do that. You may ask, why don't the other trends like radius, atomic radius, and electronegativity show these exceptions? If you look at them, they don't show the same little dips that we saw in the ionization energy and the electron affinity. And the reason is that these trends are measured on atoms, but they're actually measured when things are bonding. So when things are sharing electrons, and when things start to share electrons, their atomic orbitals change into something new. But it means that those really specific detailed things about atomic orbitals, like P's versus S and P4 versus P3, those things don't have the same impact on electronegativity or atomic radius. So there aren't any funny exceptions to these trends. They just either go down across the groups or they go up across the groups. So you only have to explain exceptions for ionization energy, but you should be able to explain either one of these very specific exceptions in detail based on orbitals. And you should be aware of what electron affinity is, be able to represent it in an equation, and have a general sense of the trend. It pretty much mimics electron affinity in that it's getting greater and greater in magnitude up to the halogens. Okay,